Today we're working in section 9.3. This is from page 378. No, I take that back. This is number 78 in section 9.3. Bottles of a popular cola are supposed to contain 300 milliliters of cola. There is some variation from bottle to bottle because the filling machinery is not perfect. It is not perfectly precise. An inspector measures the contents of 6 randomly selected bottles from a single day's production. The results are given there. Do these data provide convincing evidence that the mean amount of cola in all the bottles filled that day differs from the target value of 300 milliliters? A couple things I want you to start to notice. Anytime you're asked a question similar to this, do these data provide convincing evidence? That's what tells you that you're doing a test of significance. If instead it had asked, estimate the amount of cola in each bottle, that's when you're doing a confidence interval instead. So be able to keep track of whether or not the question's asking you to do a test of significance or a confidence interval by looking for these key types of words, the hints that they're giving to you. The other thing is that they're telling us that we have a mean amount. So as soon as you read there's a mean, you should start thinking of doing a t-test and having a t-distribution. Then from there, you're going to want to keep track of everything that goes along with it. So we're checking to see if it differs from the target value of 300 milliliters, because that's what we're looking for. That's where we're going to get our hypotheses from. So we have our null hypothesis of mean is equal to 300 milliliters against our alternative hypothesis that the mean is not equal to 300 milliliters, again because we're just checking to see if it differs. Then we've given our parameter of interest. We've defined the mu that we're using here, where mu is the mean amount of cola in all the bottles filled that day. Now along with this, I want to give my alpha level. It's always easier for me to make a decision if I have an alpha level set from the beginning. It wasn't specified, so I'm going to go ahead and use the most common alpha level of 0.05. From there, I move into checking my conditions. Remember, we always have 3 conditions. We have our SRS, we have our independence condition, and we have our large counts condition. So in this case, we know, I'm going to move this so you can see the top better. We know there were 6 randomly selected bottles. Then we would want to check to see if each bottle is independent of one another. If we're not sure, we can check 10%, and 6 should definitely be less than 10% of all the bottles filled that day. Then the last thing that we check for is our large counts condition, or really what we're looking for is normality. Now, you definitely know that 6 bottles is not a large amount, so we're instead going to check for normality. Remember, in the t-distribution, though, we don't need it to be perfectly symmetric. We basically need there to not be outliers and not be strong skewness. But due to the fact that this is such an extremely small sample size, we definitely want as perfect to symmetric as possible. So, again, I forgot to bring my calculator home this weekend, so I'm going to have to go off of my phone. I put all my data into the list. After that, I'm going to look at histograms. Usually going to give you the best picture of shape. So I'm going to graph this using a histogram. Whoops, sorry. It should be zoom 9. Okay, so looking at that, that's not giving me a great picture of what's happening here. It looks almost uniform except for this big one. So because the histogram isn't giving me the best picture, I'm going to take a look at it a second time. And I'm going to switch instead to doing a box plot. In a box plot, I can definitely say there's no outliers. And these whiskers are almost identical. This box might be a little bit bigger than that box, but it looks like it's pretty well symmetric. So I'm going to go ahead and say that's probably fine for me to use. And part of my answer is going to include a drawing that looks just like that box plot there. Okay, so I've included a picture of my box plot in my answer. I also went ahead and found the median, which came from my box plot, and I did the 1 var stats to get what my mean is as well. Now, because those are almost identical, that tells me that this graph is pretty close to being symmetric. So looking at the box plot and comparing the mean and median, the sample seems mostly symmetric with no outliers. Therefore, I can use a one sample t-test. Now going through my one sample t-test, I know my x-bar, I just found it there. Part of that one var stats that I did, I also was able to get my standard deviation, which is 1.5029. Both of these came from doing one var stats in the calculator. Then I can find my t-score, which is my observation, minus my mean, that comes from my null hypothesis, divided by my standard error, which is 1.5029, divided by the square root of n, so that's going to be divided by the square root of 6, and that gives me a t of negative 1.58. Now again, I can do this either using table A or actually table B for this, or I can do it in the calculator. So in the calculator, here I was with my one var stats. I'm going to go to stat, over to tests, down to a one sample t-test. Okay, oh, I take it back. It just says t-test in the calculator. And then I'm going to say that I have actual data. My null hypothesis is that mu is equal to 300. I put my data into L1 already. The frequency is 1. My alternative hypothesis is a not equal to. And then I'm going to calculate. If you ever wonder, the draw actually makes a drawing of the curve. If you want to look at it, you can do that. But I usually just go straight to calculate. Now I'm going to take out all of this information that it tells me. I already knew my t was negative 1.58, but I'm going to write down my p of 0.176. I have my x bar already, I have my sx already, and I have n equal to 6. So I use that to make my conclusion. My p of 0.176 is definitely greater than my alpha level of 0.05, so that tells me I'm going to fail to reject. So I'm going to write that in the context of the problem. We do not have statistically significant evidence that the mean amount of cola in all the bottles filled that day differs from 300 milliliters. And that would be the end of our problem. Remember, going from stating our hypotheses to checking our conclusion, checking our work, checking our conditions, showing our work, and finally making a conclusion.